Okay. Alright, so when you have two molecules of water, you can get a hydronium ion and a hydroxide ion, and the hydronium ion occurs at very low concentrations. So there is an equilibrium that exists between water that is unionized, as seen right here, and the hydronium and hydroxide ion. So water is not going to dissociate very much, so we're going to see a much higher concentration of intact water than we're going to see the hydronium and the hydroxide ions. So we say that Kw, which is the equilibrium constant of water, is going to equal 10 to the power of negative 14, but writing 10 to the power of negative 14 is a little much, and so we're going to take the negative log of these types of values and place a letter P in front of it. So we get pKw, pH, and pOH. And just remember that pKw is going to equal pH plus the pOH, which is going to equal 14. So an acid is going to donate a proton in solution, while a base accepts a proton in solution, resulting in conjugate acid-base pairs. So as we can see right here, acetic acid is going to donate a proton, and then it becomes a conjugate base once it does not have that proton anymore. So a drug can remain unionized or ionized depending on many different factors, and they are going to behave very differently depending on whether or not they are ionized. Alright, so this is pretty self-explanatory, so I'm not going to go through that. Hey, remember that non-electrolytes are going to not form ions in solution, while electrolytes will form ions in solution. So most drugs will fall into the weak electrolyte categories, meaning that they will partially ionize. So for example, aspirin is weakly acidic, meaning that it is a weak electrolyte. So some of it will exist in its charged form, but most of it is going to be the unionized, intact form of aspirin. Right? Like we said before, strong acids and bases are going to completely ionize at all pHs, so they're going to be pH independent. And then the next one, we're going to see aspirin again. Remember that it's a weak acid, so it's going to donate a proton, as seen right here, and it's going to become a charged negative ion, or basically the conjugate base. So when we dissolve aspirin into a glass of water, you'll see that the concentration of hydrogen ions increases because aspirin is a weak acid and it's going to lose a hydrogen ion, and this in turn is going to decrease the pH. But if we had a strong acid, we're going to note that the decrease in pH of the solution is going to be way more drastic because strong acids are going to completely ionize, therefore we're going to see more hydrogen ions floating around in the solution. Also, just know that aspirin at a pH of 8 would ionize more than aspirin at pH 4 because it's a weak acid and the degree of ionization depends on the pH. So to calculate pH, the easiest way is to just take the negative log of the hydrogen concentration. So in this example, they already give us the concentration of the hydrogen ions, which is just going to be 0.001. So taking the negative log of that, we're going to get 3. And then for the pOH, we're just going to subtract 3 from 14, giving us 11. For weak acids and bases, we're going to either have to know the percent dissociation, or we're going to have to know the Ka or the Kb value. So here in this example, we have a weak acid, and remember that weak acids aren't going to completely dissociate, and so we can't just take the negative log of the 0.015 concentration. We're going to need to know the percent of hydrogen ions that are going to be dissociated in the solution. So we're going to multiply this value and this value together. That's going to give us 0.00225, and this is going to be the hydrogen ion concentration seen in this solution once the weak acid dissociates. Taking the negative log of this number, we're going to get 2.6. So a weak monobase has a concentration of 0.02, and it is 20% dissociated. And so the pH of this solution, again, we're going to multiply the percent dissociation by the concentration, giving us 0.004. And this is the hydroxide concentration, not the hydrogen concentration. So when we take the negative log of that, we're going to get 2.39, which is the pOH. And to get the pH, we're going to subtract 14 by 2.39, giving us the pH of 11.6. So again, we already went over percent dissociation, but now we're going to go over the Ka and Kb values. So this is just how we're going to calculate the pH with these type of values, and this is just going to, I'm just going to explain how we derive this equation right here. So right here, we're going to see the basic equation of how a weak acid is going to dissociate into the hydrogen ion and then the conjugate base. So Kf is the equilibrium of the forward reaction, while Kr is the equilibrium of the reverse reaction, and the rates are going to be the same. So we can get this equation right here: Kf times Ha is equal to Kr times the hydrogen concentration times the conjugate base concentration. If we rearrange this equation by dividing each side by Kr and dividing each side by Ha, we can get this equation. So just note that Kf divided by Kr is actually equal to Ka. So if we rearrange this equation once again by dividing each side by Ha, we get this equation. And also note that the weak acid concentration is basically going to be the starting concentration, because remember that weak acids don't dissociate very much, and so that concentration is basically going to equal the starting concentration. So we can replace Ha with C. And also just note that the concentration of hydrogen ions and the conjugate base ions are going to be the same, and so we can basically just do Ka times the concentration, original concentration, is equal to the hydrogen ion concentration squared. So once again, rearranging this equation again, if we square root both sides, we're going to get this equation, and then we're going to take the negative log of each side of this equation and get this final equation. This is the equation that we're going to be using to calculate the pH when we have pKa. So compared to a weak acid, a relatively strong acid is going to have a large Ka value and a small pKa. So remember that Ka is equal to the ions concentration that are dissociated all over the concentration of that original weak acid. And so something that has a very large Ka value, it basically means that the original acid concentration is going to be very, very low, which means that basically the acid is going to dissociate completely, and so this top number is going to be much larger than this one, meaning that it's going to be a strong acid. Right, I guess that's all. I'll see you guys next time.